right, to stack them, right? To have
And
to have
you
U1
compare and contrast, like why?
Okay, I'll answer it the same way I did it before. I'll say, if you're trying to do this way, you're just pretending not to do the encoding, but you're actually doing the encoding underneath. You're just pretending you're not. You're hiding it, and I'm not hiding it. I'm putting it in plain sight and confusing you all. Yes?
So the label that says that tau of x is the code for b on the left side, like so on the left half of the board.
Left half of the word?
Yeah, you've got a code for b. So that's not true if we're going to follow tau, right? Because tau of x will not be able to. Like x is the label, but tau of x is not.
Yes, this is like the actual type that we can take. So yeah, I was trying to say this when you're trying to make a proper pi type, right? You're gonna say pi x in a b of x, right? And then I'm saying that actually this thing, right? I'm saying that you have a hat check, okay, and then tau of a hat check is a, okay, I have a code, and then this function here will take that and it will map x instead of, so it will not give you b of x, but it will give you the hat check b of x. Codes for b here. Okay? So this function here is taking the actual elements from the actual A, but it's not giving you the entire b of x type, but it's giving you the code for this type, because it lands in U. Okay. Now I have confused you good enough that I can actually say, well, for sigmas, it's going to be exactly the same. So for sigma, it's exactly the same. Here I have a sigma hat check, and here I have a sigma hat check, and here I have a sigma. And I'm not changing anything else because the pi's and the sigmas kind of look the same. Right? So the codes for sigma, same thing as pi. Okay? And then we have also the code for the identity type. And I already gave you the constant 3, so this one is easy. Where am I? Perfect. And then I have for the identity type, we'll have again some I head check, pi, the code in U, from tau x to tau x to U. And it's of the same kind as the other one, right? Just that I'm taking two elements for the identity type. And we have the judgmental equality that tau of I hat check x, little y is judgmentally equal to x equals y for every x in U and little x, little y in tau of x. Okay? So same idea as before, it's just that now the propositional equality will take x and y and it will give me the code for the propositional equality. Yes?
So you take, if this is kind of, you take x hatchet, you take y hatchet, and then you get x equals y hatchet.
No, I take x hat check and then I take the actual elements of the t of x.
Okay.
because x and the little x and little y are the actual elements of that we're equating. So that's why here I have t of x, t of x. Little x and little y don't have hat check. No codes. Don't make me do the example. I'm running out of time. Okay. Now, we also want to avoid the Russell's paradox, right? So, we don't want U to contain a code of itself, right? This is what we want to avoid Russell's paradox. So what instead we do is we assume enough universes, and this is a postulate, okay? I'll just copy it from the textbook. We postulate that we have enough universe. It means that for every finite list, of types in context, like this, gamma I, gamma 1, A1 type, and then gamma 2, A2 type, gamma n, gamma, an type. There is a universe U such that contains each I, in the sense that U computed in gamma I, AI hat check is in U for every I, and we have the judgment in gamma I tau of A hat check is differentially equal to AI type. Okay? So for every finite list of judgments like these, so contexts and types, there is a universe that contains all of them, all of the codes, and the decoding will give me exactly that. This is how we postulate the universes. So we start with the base universe when there's an empty list, right? And if I have an empty list, and I have a universe that is closed under all of these constructors, then I still have some codes, right? And the ones that I showed you in, for example, are inside even if I take the empty list here, right? Because I have to close on the constructors, and that includes all of these hat checks that I indicated before. So this one we call the base universe, right? For empty context, on the empty list, we call the base universe. Zero. And then we want to make the next universe, okay? And the successor universe will be the following one. I have a list of two stuff, U type, and for x in U, T of x is a type, right? So I'm giving myself this universe and its corresponding decoding function as two elements of this finite list, and this will produce the universe U plus, okay? That will suffice these two for this list, okay? So this means that I will have a U hat check in U plus, okay? The code for the previous universe is in the next universe, and then for every x in U, the tau hat check of x is also a code in U plus. define then the tau of the U plus, code the tau plus now decodes the Hatcher Q to the actual U type. Okay, so we just went one level up, and now our previous U has a code, Hatcher, and it's the actual U. And of course, if X is in U, then the tau plus of tau hat check of X will be the actual tau of X type. Okay, so here I have three T's, or taus plus hat check, no extra add-on. Okay, and then we can make U plus plus and U plus 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 and so on and so forth. And this is how you avoid Russell's paradox by having many, many universes. Okay. One last thing I want to say about the universes here at this point is that we can also conjoin two universes, okay? So we can have, if I have two universes, U and V, I have two universes, U and V, then I can form the universe that is like a join of the two universes. Gone. A join of the two universes, U and V, and this is by obtaining this postulate by the following finite list. So if I have X mu, then Tu of X is a type, and I have Y V, then I have tau V, Y the type, and then I can form out of these two by the same construction as here, U join V. So I can, basically what I'm saying is that if I have two universes, two universe levels, right, and they're not the same, I can have a higher one that contains both. Okay, so I can always sort of, we think of this as we can embed, the types. If I say, okay, types live somewhere in the universe, right, we can always embed the types in a common universe, so we can, make constructions if it's going to be in a higher universe than if we look there. Okay. Can I have 5 more minutes or no? Yes? No? Maybe? Zena? You're the judge. Okay.
Yes.
Yes. Okay. Now, Rob has universes that are all of these, plus another one that's called prop. And I have here somewhere, okay. I have here a definition. This is like the source, this is the paper I copy-pasted these equations from. So in calculus of adaptive constructions and Martin-Löf type theory are almost the same, except for prop, more or less, okay? So this is why this is important. So the universes in ROC, calculus of inductive constructions, are all of these. So type I are the usual universes, right? The U's that I used here. And then there's a special one, prop. And the thing is that, all of the other universes, when we make function types, right, we can make function types such that, if X is of type A and B is of type I and A is of type I, then this pi here will be of type I. And, I didn't include one important one, that you can sort of embed the little ones into the bigger ones, except for prop. Prop is a special one because it has a special rule. And it basically says that if X is of type A and the codomain B is of type prop, then this is going to end up in prop. Even though this A here could be of a higher type than prop. Okay? Even if this one is type 3 and B is a proposition, then it will end up in prop. Okay? This is the impredicativity property. And the reason to do this is to sort of hide computational content where we think it shouldn't be there. Okay? So I will show you an example rather than do the full-on theory. I'll show you how it looks in practice. Okay? So here is how it looks in practice. There are three kinds of existential quantifiers in rock. There's X, there is sig, and there's sig t. Okay? And I will focus on X and sig t. So X is the existential quantifier for propositions, and sig t is the usual sigma that we saw before. And I have an example, and I will again do the root thing and copy it from my previous notes. And it will probably be wrong because the last time it didn't work. But this time, I'm hoping it will work. Okay? And this is, I'm showing you this because it's such a common pitfall. Okay? When you're trying to do something and it doesn't work, and then you change the universe and it suddenly works, and then you are really confused. So let's walk through this example together. Okay? I'm defining something called full X. And basically it says that if I have something that is of type exists X, so sorry, I have a predicate P, okay, a binary predicate P that takes something in A, something in B, and gives me a prop, so it's a binary predicate. And now if I have exists N in A, such that for all X in B, P and X, then I can have, for all X in B, exists Y in A, that's what I have P of YX. And intuitively, this says, if I have one element in A that is good for all of them, then for all of them, I can just use the same one. Okay? Let's walk through the proof together. So I'm introducing all of these things. I have A, B, a binary predicate, and a proof that says there exists an element in A such that for all X in B, P and X. Now I want to construct this type that for all X's there exists something. So I can introduce B, and now I have to provide a witness which element of A exists such that this holds. And well, I have to get it from somewhere in the context, and I don't have an element of P of something B, but I do have this exists here, right? So typically what I want to do is I want to use this witness here from Px. Okay, I want to take the one that exists and plug it into my goal. So I can say destruct Px, and now I have something in A, it's called X here, and then I can say exists X, and then I can just apply my hypothesis, specialized to B, and I'm done. Okay? So this works fine. And you can now you believe me that if I have exists something such as for all of this, then for all I can just plug the same one for the other ones. Now let's say I want to do the other thing. Now let's say I have a statement of the type that this one looks the same, I still have a binary predicate P, and I have an exists N for all X, blah, 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 such that for all X, and this is the exists, but it's sigma. This is a syntax for the sigma type, okay? So this is something in A, P, Y, X, and this is the dependent pair here. This is the dependent sigma. Now, if I want to prove this thing, if I want to do the same trick, I want to say, okay, let's just destruct here, and I will get this witness out. But it will fail, right? So I should show you that this actually fails, right? It failed, and it says incorrect elimination of in the inductive type X. The return type has sort type, while it should have S prop or prop. Okay, S prop is a separate issue, but before we had prop and it was fine. Now it's not fine. Now it demands to have type. Okay, so what's the deal? Why does it complain here? If I just swap, you see, if I just swap here for prop, if instead of the sigma I have exists here, it didn't complain. Now it complains. Why does it complain? It complains because it exists here in the context is hiding the witness. Okay? It's in prop, which means it's opaque, which means I cannot access it anymore. So if I'm trying to say, there exists something, there exists something, and then, I want to show it, which one, I cannot see it anymore. And this is the main difference I wanted to show you. So if you get in trouble because you're trying to destruct an existential quantifier somewhere, this is the reason, right? You're in the wrong universe, and you can either fix it here, that this doesn't exist, this is a sigma, right? Or your end universe here has to be prop, which is then, like we had here, exists. Okay. Who understands this example? Okay. The people who did some rock kind of understand. Okay. So come talk to me after the lectures if you want to understand it better. And thanks for letting me have the extra 5 minutes.